So for this week's update, I completed the first 30 problems of section 24, Sylow Theorems. There were 19 proofs so far in these 30 problems. I'm up to 367 proofs, 770 problems total of Gallian attempted. That's 45.6 as of September 20, 2025. I've also read section 25 on finite simple groups, which is a relatively short section. Yeah, so about halfway through the problems in section 24. And yeah, the counts are there, but I'll add counts here, and the counts for all of these for proofs and problems attempted will go all the way through the section in group theory, and then I'll come back and start on rings down here. Okay, so to the book. This has been a very interesting section. I would call it a difficult section also because non-abelian groups are painful. That's basically what I'm learning. And so you learn a lot about the conjugacy classes and some theorems having to do with them, the class equation. And I actually had to go in the interwebs and find some examples because the way Gallian explained it, it wasn't completely clear to me, but now I get it and I have done some good examples. Then in the case of the Sylow, if I said Sylow, I meant Sylow theorems. There are 3 of them. The first one has to do with p to the k dividing the order of the group G. Then Cauchy's theorem says that if p divides the order of the group, then the group has an element of that order, p. Then also there's the concept of conjugate subgroups. Then the second theorem is about subgrouping. So H is a subgroup of G, the order of H is a power of P, then H is in some Sylow P subgroup of G, just some. And then the third theorem, which for the problems has been the workhorse. I mean, I've been using this theorem for many of the problems. You take all the multiples of all the factors of the order of the group, and you mod them to the prime from the prime factorization. And if you get a 1, then there's a possibility that there are that many. So the factor itself, if the factor is 4, and I'll show it in the problem, then there could be like 1, 4, as many f's equal 1 mod p. And it has to divide m being this other factor. So it's for groups that are of type p to the k m. Yeah, order p to the k m. And then the business of finding if the p subgroup is normal. And if it's the only one, so if it's 1 mod p and all the other mods are not 1, then it is normal. And then these examples are really well done by Gallian, in my opinion, having looked through the ones in Dummett and Foote, and I'll show Dummett and Foote as well because it's relevant to this discussion. So there are examples of mucking around with specific groups of specific orders with the Sylow theorems to say things about them, and all you really need to know is the order of the group. You don't even need to know if it's abelian or not. And then there are examples that Gallian does 3, where it's about how many groups of that order exist. 2 different questions that are being answered here. And then, of course, there's also a theorem for groups of order PQ. And so you pick Q being greater than P does not divide Q minus 1, then G is cyclic. Yeah. All right, so on to the problems that I worked on. Oh, actually, I'm going to show Dummett and Foote. So in the case of Dummett and Foote, I think I almost know the page by heart because I've been looking at it so much. I think it's in here. Section 4.3, I believe. Or 4. Sorry, I should have marked. There we are. I knew I was in the neighborhood. So in the case of Dummett and Foote, they lay out the 3 theorems all within something that they call Theorem 18. So of course, number 3 is the 1 mod p one that I just showed. Number 2 is the one with subgrouping. And number 1 is that they exist for a specific order. Yeah. And so they lay out the proofs, and then they have examples. Examples of type PQ, the order of the group 30, of order 30, 12, P square Q, order 60, and then a bunch of problems. But then, and then the simplicity of AN is actually in section 25 in Gallian. But then somewhere in here in the special section on groups, they also work through the cases of some of these groups using the Sylow theorems. Using the Sylow theorems, but they're focusing more on the classification of finite simple groups. So that's the context. And so yes, they get to use them again, order 30, order 12, P cubed, and then I think they have more. Yeah, and further topics. So yeah, Dominant Foot has a lot more on Sylow theorems. This is almost becoming a video about Sylow theorems in various abstract algebra books, but I really wanted to show the difference between how much there is in Dominant Foot in comparison to Gallian, just to show. And yeah, sure enough, they use the Sylow theorems for the techniques for finding finite simple groups, and they go through a bunch of examples, and within them, especially the group of order 168. And so you will see, if you ever do any of this work, that there are, when you look for answers in the internet, you will see that some of them are only for when the order of the group and the group is simple. So in the case of section 24 of Gallian, which is what I'll be talking about in this video, they're not simple. So simple groups have not been yet introduced. That was the tail end of the reading. Yeah, I messed up this one, but I did get these two. And then in this case, I thought about it pretty hard. I thought I had a good argument, but then the book's answer was a lot more elegant. And even though I think what I said, you know, if A is a group element of even order, then A square is not in the conjugacy class of A. I did a bunch of hand waving. That was not good enough. I didn't get that. This one I did get after I worked through the quaternion group, the conjugacy classes for the quaternion group. After that, I was looking at some other problem in Dominant Foot, and sure enough, this is actually worked out as an example in Dominant Foot, but I had already done the problem, so I gave myself credit. I didn't look it up. I actually figured it out myself. Yeah, cleaner answers using better terminology. Could have done better there. Yeah, more, I was close, but not quite. The same with 9, I needed to complete, there were some steps that I did not do. Yeah, having to do with cosets. I should have used cosets within the proof. I did not do that. Yeah, in the case of 11, I wasn't close. The answer in the book, I learned from the answer. That's what happened with that. Then there was a question with order PQ, a group of order PQ, 55, and for the class equation. And this is the one where I found a great example laid out 421 on Stack Exchange. Man, was I happy, because I wasn't finding the answer for the one that I was doing, which is not what I wanted to do, but I was learning on how to do it. So you take the class equation, and it's got a trivial center, so it's got 1 in the center, and then there's 7 groups of order 3, 3 groups of order 7 for 21, and you just plug in the A's and B's, and sure enough, A and B is equals 2 is correct. Then after I learned that, I went back. This is an even problem, so the answer is not in the book. Then I went back and I worked it out. Yeah, I worked out all the cases, and sure enough, in this case, it is B equals 4. Yeah, B equals 4. Yeah, so I worked it out. And then in the case, and then the next problem asked similar questions, and I got one wrong because once again, 9 is not prime. but I got the other ones right. I got A, B, C correct. And these are all class equations. What are they called? Class equations. Yes, class equations. Yeah, I tried to work it out for this even problem 14 with S4, and eventually I did figure it out. And I didn't have to complete it. I was like, yeah, I got it. You just go back and make a permutation group elements out of D4. Yeah, and then translate them out. And there is a isomorphism. 15 I got correct. Yeah, again, this is P to the 4th M is how to read it. And so you take all the divisors for the group, you mod 2 and 3, but very important, the order of the Sylow 2 subgroup is not 2 in this case, it's actually 16. So it's got to do with Lagrange's equation. So that's something that Gallian rightfully so lays out. And then there's ways to play around with how some of the Sylow subgroups intersect when you do counts of elements. And so sometimes just by the counts of the possibilities, for example, here this is 1, 3, and 9 are the possible numbers. It could be 1 Sylow 2 subgroup, it could be 3, it could be 9, it could be 1 or 4 of mod 3. Okay, and actually, when I solved these early problems, I wasn't doing this, but after I did a whole bunch of these, I would do this 1, 3, or 9, 1, or 4. Yeah, 1, 3, or 9. And so you do counts to figure out whether it has a normal subgroup or not for a given order. Hand waved myself through this, didn't quite get it. I was somewhat close, but not close enough. 19 and 21 I was very happy about. Yes, the answer is cleaner in the book, but I got it right, and I was very happy about that. And the same for 21, I got it right. So by this time I was warm, I was laying them out, and I was figuring out how to find all the possibilities. Yeah, and then doing all the element counts. So for example, in this case, this is simple. In this case, there's obviously both of these are normal. Okay, because there's only one. There's only one. When you land in here in a group, you're in the golden zone. But when you have something like this, it could be 1 or 7. Yeah. Yeah, 25. There was a cleaner answer in the book, but I did get it correct. And then for 26, even though it's even, I believe I got it correct. Not only that, I think I answered more. Yeah, let me pull it up because I think it's very interesting. It's worth discussing. I feel pretty good about solving this problem. Okay, so 26 of section 24. Yeah, Sylow 5 subgroups of S5 are there, and find 2. How many? And so I found the first one was very easy, just the rotations, right? This is the first one. But then there are 4 more. I'm sorry, there are 5 more. Yeah, there are 5 more, and these are the 5. And so what you do is you start with any one of these. You take the first one for the rotation, and you use all of these, and you run them. Actually, no, I'm sorry. These cannot be, these are completely different. All of these are completely different. And so you just pick another one. Instead of 1, 2, 3, 4, 5, you take 1, 2, 4, 3, 5, and you take it to the 5th power. Sure enough, it's 1. Then you take the next one. So you do all the 1, 2s. And then that's how you generate them. And I believe this problem is correct the way that I did it. 27, I also got right. Yeah, more Sylow subgroups. And 29, I got right. Wife's been using stickers. I like them. When I find them, I put them on my notes. That's my new thing. Yeah. Yeah, 29, I got correct as well. So yeah, by now, I think I have a system for how to do these problems, and that's great.